Hello everyone. Today we talk about some important topics of the thermodynamics: entropy, first law, second law, third law, and partial molar quantities, and what are the reason spontaneous change like that. Okay, so the first law. So the first law is d equal to q plus w. It suggests engine can run in a cycle and convert heat into a useful work. Okay, that is the first law. Okay, for a cycle process d equal to 0, then q equal to minus w. Okay, so q is the heat added to the system and w is the work done by the system. Okay, minus w means the work done by the system. Okay, q plus q means heat added to the system. So it says that you can convert heat into work in a cyclic process. Okay, but the second law is put restriction on useful conversion of heat into work. Okay, what is second law say is you cannot convert heat into completely into work. Okay, that is the second law. Okay, and it also determine the direction of spontaneity, how the direction it will go forward or backward. Okay, if you take a reactant and it goes to the parabolic side, or it are simultaneously in the reverse side like that. Okay, and determining equilibrium state of a system, whether the system attained equilibrium or not, like that. So so it's a very important law. Okay, so we see. So heat reservoir is nothing but a very large system with a uniform temperature which does not change regardless of the amount of heat added or withdrawn from the system. Okay, so also called heat path. Okay, okay, we saw the different statement of the second law. First, the Kelvin statement. So what the Kelvin says is you cannot convert heat into cannot. It is impossible for any system to operate in a cycle that take heat from a hot reservoir and convert completely into work. So the main point is you cannot take heat and completely convert it into work. Okay, that is the main point. Okay, uh, in a cyclic, the system runs in a cycle. Okay, so then what happens then? Some amount of heat is transferred into the cold reservoir. Okay, so the heat added to the system is q1, some amount of heat is added to the cold sink minus q2, and some amount of work is done by the system minus w. Okay, then this is possible. Okay, q1 equal to minus w minus q2. So the q1 added is not equal to minus w, some heat is lost. Okay, so heat is also energy, work also energy, joules energy. Okay, the unit is joules, heat is also joules. So some, if you take 10 joules heat means work is 8 joules. Okay, so if you take 8 is minus 8 joules, work is done means minus 2 joules is added to the uh, cold sink. Okay, so then the equation cancel out. Okay, becomes 0. Okay, like that. You cannot convert 10 joules to 10 joules work. Okay, that is impossible. Okay, what is the classiest treatment? So same, the it is cycle. This is important. Okay, so the system operate in a cycle that takes heat from a whole reservoir and transfer it to hot reservoir, like in refrigerator, because in the room or in the refrigerator in the cold reservoir. Okay, so it take heat from the cold and transfer it into the hot. Okay, hot reservoir, that is the surrounding. Okay, that is impossible. Yeah. So here, if you heat q2 is the heat added to the system and q1 is leaving the system, it is impossible. You should add some work. Okay, you should add some work. So for refrigerator cannot uh, work in spontaneously. Okay, you should connect with the electricity, and the electric work is here used. Okay, here the work input is the electric work in the refrigerator. Okay, so you take the heat added to the system W, and the heat added as work is W, then only you take minus Q1, that is the heat taken outside. Okay, so how much heat is taken from the cold sink. Okay, so these are very important calculations. Okay, very important statements. Okay, for the alternative statement of class A statement is all spontaneous processes are irreversible. Okay, so we prove in later slides. Okay, heat flow from hot to cold spontaneously and irreversibly, but cannot the opposite. Okay, the opposite is not true. You cannot flow heat from cold to hot. Okay, spontaneously. Okay, So mathematical statement. So for integral of circle means it is a you integrate over the cyclic process. Okay, dq reversible by d equal to 0, but the dq irreversible is less than 0. Okay, so don't confuse. So this is the integral of dq reversible by d is a state function, that is the entropy. This is the definition of entropy. Okay, so we see um, so entropy is nothing but the dq divided by dq reversible, the heat added reversible divided by temperature. Okay, so what is Clausius inequality? Okay, um, the work done when a change is reversible, that is more when the change is irreversible, the you can get more work from when the system is in reversible change. Okay, it compressed or expands. Okay, uh, what it take expands, the system does work means first take, if you system does work means the both are negative. Okay, so then take the dw into that, take left side to right side, you get these relations. Okay, so the internal energy is a state function, so it does not change whether the path is reversible or irreversible. So du equal to same for irreversible and reversible. Okay, just to rearrange this equation, you get this. Okay, then we know this is greater than or equal to 0. Then this should be also greater than or equal to 0. dq reversible minus dq also greater than or equal to 0. Then take the dq that side and you get this relation. Okay, so just to divide both side by temperature, you got this. So this is the definition of entropy. Okay, this is the definition of entropy. Delta S dq by reversible by d is a delta S. Okay, definition of entropy. So this is for reversible. Okay, so for irreversible, this is dq by dt. So that is somewhat greater than the reversible. Okay, somewhat less than the reversible process. Okay, so this is the Clausius inequality. Okay, so then if you take an isolated system means q equal to 0, then delta is greater than or equal to 0. Then isolated system entropy only increase, cannot be decrease, only equal to 0 or greater than 0. Equal to 0 when the process is reversible, greater than 0 when the process is irreversible. So the Clausius statement also states that spontaneous process are irreversible, necessarily irreversible. Okay, it should be irreversible. Spontaneous process should be irreversible. How they prove it? If you take delta S total equal to delta S system plus surrounding. Okay, what is delta S system? dq by dt. D. Okay, so what is delta S surrounding? The same heat. Okay, so if some amount of heat is added to the system is means the some amount of heat is lost from the surrounding. Okay, so then only it comes from nothing. Okay, so it cannot magically blown into the system. Somehow heat added, somehow system gains energy means somehow the surrounding lost energy. Okay, so that is, this is minus dq by dt. Okay, that is the entropy of the surrounding. For the system, yeah, dq by, for reversible process, the system's entropy is dq by dt. Okay, but for irreversible process, it is greater than dq by dt. Okay, so if it is greater means the positive sign is somewhat greater means we get as positive. Okay, so that is the concept. So for irreversible process, uh, spontaneous process always irreversible. Okay, so that is the conclusion from the Clausius inequality. So these are very very important. Okay, so for further calculations are like that. Okay, we saw, you see these relations. Okay, simple mathematics, you refer. Okay, then so we take a Carnot engine. Okay, so take a Carnot engine. So first you take a system. Okay, you take a system and you contact with the hot temperature. Hot. Okay, hot temperature means the heat is flowed into the system. Okay, heat is flow into the system from hot source to system. That is then they start to expand. So this is the volume. Okay, so start expanding. So that is the isothermal expansion, because it is temperature constant. Okay, hot source is temperature constant. Okay, then if you take and then cut the source of hot and take the system isolated, then also the system try to expand. Okay, try to attain equilibrium because it attained heat. Okay, then if you take isolated means the heat acquired is try to expand, okay, try to expand, okay. That is the adiabatic expansion. Then you take the same system into contact with a cold reservoir, then the heat is from the system to surrounding, okay. So now what happens is the system try to compress, that is the isothermal compression, okay. Then if you cut the source of cold, then go the adiabatic compression, okay. So adiabatic mean q is equal to 0. So what is efficiency? How much you heat put input gives and how much you get the output. That is the efficiency. Okay. The heat input is Q1 and the work output is total work heat input is Q1 from the hot source. Okay. The total work output is the add the four process work. Okay. From the first law, du equal to 0 means Q equal to minus W. Substitute this from this, you get this relation. The q is less than 0, okay. So because q is left to the system, okay, q is left system to the cold sink, okay. So this is negative means 1 minus negative means 0.5, like that means you got a zero point 0.5, okay, always less than 1, okay. So efficiency always less than 1 means less than 100%. You cannot get 100% efficiency, that is the second law, okay. So negative work equal to q1 efficiency. If efficiency equal to 1 means the heat added is completely convert to work. If it is always less than 1 means you cannot completely convert heat into work. That is the second law, okay. Note, if a cycle run in reverse, like in a refrigerator, the sign only change, okay. Q1 become less than 0, Q2 greater than 0, W is greater than 0, okay. For Carnot engine, for ideal gas, same. For ideal gas, same. The formula only changing, okay. For ideal gas, isothermal process means delta U 0, Q equal to minus W, and W is nothing but PdV, and P is nRT by V, like that, okay. So you know the relations. So reversible adiabatic process. For reversible adiabatic process, this is the relation, okay. The temperature and volume relation. Yeah, we saw V T whole power C equal to constant, okay. That is the relation. Or PV whole power C also is equal to constant, okay. Okay. So these are two relations for adiabatic expansion, okay. So okay, then the relation you see, this is d1 by d2, this is d2 by d2. Just changing the, just reversing this, not changing nothing. Okay, so just changing this, you got these two become equal. Okay, these two become equal. What we want is q2 by q1. Okay, q2 by q1 is t2 ln. So this is from relation. Okay, this is q2 q1. This is q2. Okay. So we want q2 by q1, okay. So then replace by this relation. From this relation you got you gamma minus 1 cancel out gamma minus 1, you got this, and from you got v1 by v2 equal to v4 by v3. So you can substitute for v2 by v1, you can substitute for v4 by v3, then you got a negative sign, okay. So if you want v2 by v1 equal to v3 by v4, okay, like that. So just changing the position in the lawn, you got a negative sign, okay. So that is this, the simply is q2 by q1 equal to minus t2 by t1, okay. So take this outside, you got this, that is the cyclic process dq reversible by t equal to 0, okay. um, Okay, so you can replace this same result now. Okay, some temperature approaches 0 Kelvin means this is become 0, then efficiency become 100%, but that is not impossible. Okay, so this is our important relation. So for heat engine, total workout equal to minus W psi into Q1 equal to T1 minus T2 divided by T1 into Q1. So W1 always less than Q1, okay. So only in the limit of T2 approaches 0 Kelvin, W1 approaches Q1 and efficiency approaches 100%. Conversion of heat into work, okay. So third law will state that we cannot reach this limit, okay. For a refrigerator, Q2 is greater than 0, W greater than 0, T2 less than T1, okay. So then the total work in is W is equal to T2 minus T1 divided by T1 into Q1. Okay. Then take this relation. Here, if temperature becomes zero means here below the temperature zero. Okay. Something below zero means you got infinity. Okay. 1 by 0 equal to infinity. Okay. So work become infinity. Okay. So what is this means is if we infinite amount of work needed to extract heat from a reservoir at 0 Kelvin. Okay. That is, so third law says you cannot reach the 0 Kelvin. Okay. Okay. For entropy for a reversible adiabatic ideal gas Carnot cycle efficiency formula. So these are different formulas, same. Okay. So efficiency, these are very important. Sometimes they give the heat. Okay. Sometimes they give the temperature. You should know the difference. So what is heat, what is the temperature? If this is hot source and this is cold source, the temperature of hot source is T1, temperature of cold source is T2. Okay. The heat from the this is Q1 and this is system means this is Q2. Okay. So you know what is Q1, what is Q2. Okay. Sometimes they give TH means the temperature of hot source, TC means temperature of cold source. Okay. Okay. Okay, some assume. Okay, efficiency of any same as efficiency of any reversible engine has to be same as the Carnot cycle. Okay, we can prove this with the example. Okay, so this is somewhat complicated. Then so take this. Okay, this is easy. Okay, easy to understand. Okay, if hot source at higher TH temperature and cold sink at a TC temperature. This is a like Carnot engine. Okay, this is like a heat engine. Okay, it takes heat from the hot source and convert into heat work and leave QC amount of heat into the cold source. QH is the uh, temperature from the hot source. Okay. So okay, so first we assume A is higher efficient than efficiency of A is higher. This engine's efficiency is higher than the this engine. This is like this follows the Clausius equation. So it takes the same amount of QC from the cold sink and return back to the hot source. Okay, uh, how much A gives QC and take backs into this engine's efficiency is very less. Okay, so it needed heat. Okay, so this engine needed heat. Okay, so you should add heat. The A gives heat. Okay, so this heat is transferred to this, but it is higher efficient means some amount of work is released to the surrounding. Okay, only if it is 50% work needed means 50% work we got. Okay, the total conclusion is you take a heat and you convert to work. Okay, without adding to the cold sink because that amount heat is taken back to the hot source. Okay, so this is somewhat contrary to the second law. Okay, and then the conclusion is the first assumption is wrong. Okay, you cannot have all Carnot engines efficiency is same. When the temperature of hot and cold are same, then the efficiency of A and B are same, should be same. Okay, so that is the formula. So if it is not same means it violates the second law. Okay, that is the conclusion. Okay, so for any irreversible engine only the efficiency depends on the temperature difference between T2 and T1. Okay, does not the engine's efficiency does not change. Okay. Okay. So entropy is a same. The entropy is a state function, but to calculate entropy requires a reversible path. Okay, we see the examples later. Okay. Okay, for irreversible Carnot cycle is less efficient than the reversible one. How? Uh, we know before we saw the reversible work is greater than the irreversible work. Okay, so then if you take this, the irreversible heat is less than the reversible heat. Okay, because this entropy is a state function. Okay, what happens next is if you put this in q1 reversible and q irreversible, this is negative. Okay, so here this is less than means the whole term efficiency become less than. Okay, so reversible engines efficiency is less than the see irreversible engines less than is less than reversible. Okay, so simple mathematics. In the below is less than means the above the total value is high. Okay, so it is negative. Q2 is negative. Okay, so 1 minus like 0.5, like 1 minus 0.8, 1 minus 0.8. So something bigger. Okay, so you, when you get to 0.5, 10 divided by 2. Okay, when you got 0, if you take 0.8 means something simple. Okay, so take something simple means 5. Okay, 2. Okay, means 10 by 5. Okay, you get 0.2. Okay, when the below value is high, here q is high. Okay, so when the below value is high, you got 0.5. So that is simple mathematics. If you don't, if you done the message, you know the concept. The concept is when the reversible engine's efficiency is lesser. Okay, irreversible. So this is the classes inequality for reversible, for irreversible. So entropy often never decrease isolated system again. So if you find entropy of an system 1 to 2 irreversible process, you should take the system back to the 1 by an irreversible process, because entropy is a state function. State function means path of delta S equal to 0. Okay, mean for a cyclic process it is same. Okay, so if it for the process A is delta A, okay, delta S A minus delta S B equal to 0, should be 0, because it does not depends on the path. Okay, that is a formula. So if you want to find the delta S A, means you should take the system back to the initial state, then calculate for the reversible process, then only you can calculate the for easily find the for irreversible process. Okay, okay. So okay, for if you take an example, you know for path AQ equal to 0 for isolated. Okay, then classes inequality says um, less than irreversible means this is 0. Okay, so only we got the 0 to 1. This is the entropy of system A plus delta is equal to 0. Okay, okay, taken back to the system equal to 0. So this is irreversible, this is reversible. Okay, um, so when first process is isolated system, so q irreversible is equal to 0, so the first becomes 0, then the second only can less than or equal to 0. Okay, that is nothing but minus delta S, because the system is 2 to 1. Okay, delta S is nothing but delta S2 minus S1. Here you got S1 minus S2. So minus delta S less than or equal to 0, so delta S is greater than or equal to 0. Okay, this gives the direction of spontaneous change. Okay, okay, you know delta S always should be greater than equal to or equal to 0, cannot be negative. Okay, for spontaneous change. So this is for isolated system, delta is 0, greater than 0 is for spontaneous and irreversible process, equal to 0 for reversible process, and less than 0 is impossible. So less than 0 is impossible. Okay, delta is independent of path. Okay, so but the delta is surrounding is depends on whether the process is reversible or irreversible. Okay, how, because delta S may be independent of path, but the delta S surrounding depends on whether the process is irreversible or irreversible. Because delta S surrounding, how you calculate the delta S surrounding? Delta S system plus surrounding is the uh, delta S total. Okay, surrounding is the delta S total. Delta S total means delta S system plus surrounding. If the delta S system, you got different equations. So first we talked for delta S equal to dq by dt when the system reversible, and irreversible for the, so then only the system surrounding depends on the whether process is reversible or it change. When the system reversible means the surrounding change. Okay, so when is reversible means these two are equal, system and surrounding. Okay, irreversible process. Okay, consider the universe as a whole isolated system, then the system plus surrounding is greater than 0 for irreversible process. For a reversible process, this is same. Okay, so delta is surrounding and delta is system is same. Okay? So if I take an example, mm, if two are initially at different temperature and delta S1 plus delta S2 change in temperature, this is entropy change for system 1 and entropy change for system 2. This is dq1 by 2 T1 and dq2 by T2. So this is minus because the heat leave from the system. Okay, so then this is same amount because the whole system are isolated, so you cannot heat escape. Some amount of heat leaves the T2 is should go to the T1. Okay, that is my dq1 is minus dq2. Okay, then you get the relation. And then if your T2 is greater than T1 means the dq1 is greater than 0. So if T2 so like if temperature T2 is high means the heat flow from the system to, okay, so that is the from dq1. Okay, so if here you put d2 is greater than means you got a positive sign. Okay, that is dq is positive. So if t1 is greater means uh, negative sign. Okay, so then you got dq negative, and then both system the heat flow from hot to cold. Okay, just to pass and ponder. Okay, okay. One molar. So we take Joule Thomson expansion. We already saw gas at volume V and expanded to vacuum at volume V. Okay, vacuum's volume also V. So initially it is one volume, but become two volume. Okay. Delta S equal to minus delta S background. Okay, how much backwards. So if you take the system 1 to 2 means you should take the system back to, okay, so compress isothermally and reversibly back to the initial state. Okay, this is 1, this is 2. Okay, this is the isothermal compress and reversible. So reversible process, for isothermal process q not equal to 0. So for entropy, backward entropy, you find backward entropy, and dq reversible is dw, and dw is nothing but pdv, and pdv, and minus dw equal to pdv. So p equal to rt divided by v into dv. So dv here also temperature cancel out. You got r. So this is for delta s background. Delta s is just the negative. So negative r ln 1 by 2. That r1 by 2 is delta s. Okay. So if you change the 1 by 2 to 2 ln 2 means you got positive sign. Okay, because 2 power 1 means the 2 power minus 1. If you take the minus 1 back front, you can take that is logarithmic form. So you get r ln 2, that is positive. Okay, so spontaneous. Okay, so expansion into a vacuum is spontaneous and irreversible. Okay, so then something mixing of ideal gas. So Na moles of gas and it volume AVA, and Np moles of gas B and volume B, then spontaneous mixing. Okay, so, then if you take the partition is spontaneously mixing. So then we know the reversible path back to the initial state. How we can achieve it? So take it piston. Here also this piston is permeable only to B. This piston permeable only to A. So if you push that piston, you can separate A and B separately. Okay, you back to the initial state. Okay, okay. So first you for the demixing process delta U equal to 0, because isothermal process Q equal to minus W. W is PdV plus PdV for two gases, and delta is demix equal to, so PdV substitutes for PdV RT divided by V. Okay, so you got this equation. Then in terms of mole fraction is nothing but number of moles of A divided by total moles N. Okay, so in the ideal gas, number of volume of A divided by total volume, this is the mole fraction. Okay, so substitute these two in this equation, you got this relation. And for delta is, this is for data demixing the gas. For delta mixing, just to put the negative sign. Okay, okay. For x the mole fraction are less than 0, then the ln is less than 0, then the whole value is positive. Okay, always positive. Don't just see negative here. Don't come with the conclusion delta makes less than zero. Okay, because here are the mole fractions. Mole fractions are less than zero. Ln less than zero means negative. You get negative. So negative become cancel out and you get a positive value. So always mixing is spontaneous. Okay. Okay, and entropy is more mixed, is there is more entropy than the demixed state. Okay, the general result is entropy is the measure of disorder of the system. For an isolated system, entropy greater than zero means spontaneous, zero means reversible or no change in the disorder. No change in the disorder means not equal to, because delta S means change in entropy equal to zero means no change in disorder. S equal to zero means then entropy is becomes zero. I mean there is no disorder at all because delta S is change in entropy. Okay, less than zero is impossible. Okay, because you can order cannot happen in isolation. Okay, in isolated system. Okay, okay, though the always universe tends to become maximally disordered state. Okay, examples, some of the example. First we saw the mixing of ideal gas, we already saw there. Let's say then heating means heat the system to temperature T1 to T2. Okay, um so dq delta S is dq reversible by t. Okay, constant volume means w equal to 0. W0 means delta u equal to q plus w, and w0 means delta u equal to q. For a gas, ideal gas, delta u equal to cv dt, also cv dt. So you can put instead of q you can put cv dt. Okay, so if cv is independent of the temperature of the interest T1 to T2, you can take outside and you get ln T2 by T1. Delta is greater than zero when the here positive. Okay, so if opposite happen, it become less than zero. Okay, irreversible space change at constant pressure and temperature. If you take water at 100 degrees Celsius and 1 bar to gas. Okay, so it is because water becomes vapor at 100 degrees Celsius and 1 bar. Okay, uh, if it is this is very important questions when favorite question for interviewers. Okay, so if 100 degree you can, if you interviewer ask you can boil your water at 60 degrees Celsius or boil your water at room temperature. How is it possible to boil your water at room temperature without providing any heat? Okay, it is possible. Okay, so the simple relation PV is equal to nRT. Okay, if you want to boiling temperature, decrease the temperature of the boiling, you should decrease the pressure. Okay, means you try to vacuum. If you box contain your water, take the air out of it and try to become more vacuum. If it become more vacuum, if you try to become pressure, then the temperature increases and the water start to boiling. Okay, so okay, so that is if you want to boil your water in more temperature, not in 100 degrees Celsius, more temperature, like 120, like 120 degrees Celsius, like that. You should increase the pressure. If you want to increase the temperature, you also want increase the pressure. Okay, like in the pressure cooker. In the pressure cooker, they by increasing the pressure, by increasing the vapor, the water vapor increase the pressure. Okay, by increasing the pressure, they tend to increase the temperature because water is boiling point 100 degrees. So if it is open and you get how much heat you put, the water temperature cannot go beyond 100. Okay, it can vaporize it, but the temperature cannot go beyond 100 degrees. But if you put but if you close it like in the pressure cooker, the pressure increases, the temperature increases beyond 100 degrees, maybe 120 or 110, like that. Okay, that is the purpose of pressure cooker, increasing the temperature. That's why the products cooked very much. Okay, okay, pressure also increases because the temperature also increases. Okay, okay, so okay, so the here the heat is delta HVP. The heat added at the constant pressure is the delta H vaporization. Okay, so delta S is nothing but Q by dV. Okay, and the dV is the boiling point at temperature at 1 bar. Okay, So irreversible space change at constant temperature and pressure. Okay, if you put your water at 10 degrees Celsius on 1 bar, like in your refrigerator, it spontaneously become what ice. Okay, we need to find a reversible path between the two states to calculate the delta S. First, you should take the water and you already told this is very important. You always need to find a reversible path. Okay, okay, then only you find the irreversible path. Okay, dq irreversible and heated to the 0 degree Celsius. And now the 0 degree Celsius is the phase transition temperature. Okay, that is the melting temperature of or fusion temperature of ice. Okay, then ice liquid ice becomes solid and to take back to the minus 10 decrease the temperature. Okay, here. Okay, so then the entropy, total entropy is entropy of heating, then the entropy of fusion, and then the entropy of cooling. Okay, fusion is liquid to solid is fusion. Okay, then take the temperature T1 to T fusion, CPDT divided by T, plus the phase transition is minus TH fusion divided by T fusion, and take the system T fusion to the temperature T1. Okay, that is CPDB. If you change the integral of this, you get negative sign here, and you can take this inside and T1 to T fusion dt by dt. So this is the general formula. If the CP is independent of the temperature of the interest, then you can take outside. Okay, the CP not necessarily independent of temperature for the whole range of temperature. Only when the temperature interest T1 to T fusion integral law, then you can take outside. Okay, fundamental equations, absolute entropy under that law. Okay, what is fundamental equation? Fundamental equation relate functions of state, okay, to each other using first law and second law. Okay, um, uh, like if you take a first law, d equal to dq plus w is minus p dv. Okay, here you see that dq, this is a function of path. Okay, it is function of path, so you should convert this to into function of states. Okay, that is the fundamental equation. The how do you set when ds is equal to dq by t. Okay, and then take the ds here. You got dq reversible here, tds. Okay, tds equal to dq. Okay, okay. So that is the process. For a reversible process, p external equal to p and dq is equal to tds. Substitute these two, you get the fundamental equation. So this is a function only on state variables. Okay. Even though this equation for demonstrated for a reversible process, the equation is always correct and valid for a closed system. Don't forget, we find the equation for open system in the later slides. Even in the presence of irreversible process, this is because entropy, temperature, internal energy, pressure, and volume are functions of state independent of the path. Okay, so the best natural variable for the internal energy is S and V. Okay, S is the entropy, V is the volume. Okay, that is the variable. So this is a function. If you can from this you can derive this. So if at a constant volume it becomes zero, dV becomes zero. Then dou u by dou s at a constant volume is then take the ds here, you get the temperature. Okay, like that. If you differentiate with respect to volume and kept it entropy constant, mean this term cancel out and you get the negative p. Okay, you can write similar equation for enthalpy also. So enthalpy is minus u plus pv and difference dh equal to du plus dbv. dbv is pdv plus pdp. Okay, this is differentiation. Okay, then put for du is equal to tds minus pdv. Then the pdv and this pdv cancel out, you got tds plus vdp. The natural value for h are then s and p. Okay, here the ds and the dp, that is the natural variables. So by making these two constant, dh becomes zero. Okay, so at a constant entropy and constant pressure, delta h equal to zero. Okay, not okay. So you see like that from the delta h also you can write equation like that. This is same equation for the constant volume it becomes zero, and differentiating with respect to temperature, what happens? Dou s divided by dou u divided by dou t. Okay, this is the equation. Dou u divided by dou t at a constant volume. Okay, at constant volume this becomes zero. Then here also t into ds. ds mean dou s divided by dou t. Okay, differentiating s with respect to temperature. Okay, at a constant volume, the temperature become this side become 1 by t. Okay, so simple mathematics. So this is nothing but cv. Dou e by dou v dou t at constant volume is cv. Okay, cv by t. Like that, if for dh, this is equation. Absolute entropy for an ideal gas. From d equal to then take ds, and then at constant temperature du equal to 0, then du becomes 0, then this, and ideal gas pv is equal to nRT, put for nr by v. Then for at constant temperature dpv equal to pv equal to nRT. Okay, for ideal gas. Then take the n and r outside, you got dt. Okay, at a constant temperature dt equal to 0. Okay, so what is dpv? Dpv nothing but pdv plus vdp, that is equal to 0. So pdv equal to minus vdp. Then you take the volume here, and dv by v equal to minus dp by p. Okay, so you can substitute here, you can substitute for dv by v, you can minus dp by p. Okay, okay. So we delta s is delta s initial, final minus initial. Okay, this is the final pressure, this is initial pressure. Delta s is the s2 minus s1. Okay, so this is the s1, and you can take the negatives and then that side, so that is equal to minus this is, and you can take s2 equal to s1 plus s1 negative, and p0 to p0, so that is so simple mathematics. And you take the n outside, and 1 by p is nothing but ln p. Okay, so ln p by p0. If you defined p0 at constant, p0 is the initial pressure. If you define the initial as 1 bar, then this become p. Okay, p in bar. Okay, so simple mathematics. Suppose we had entropy at 0 Kelvin. How to calculate is from this relation. Previously we saw this relation. Okay, so how to calculate entropy at a particular temperature? This is, if it temperature of interest is this, how to calculate entropy? You should come from 0 to, okay, but take a solid at 0 Kelvin and 1 bar, and take to temperature of melting. Okay, and that is the entropy. So here take to entropy melting, and at the melting temperature phase transition happens. That delta S is delta H fusion by T. Okay, and then take the system to liquid to boiling temperature TB. Okay, then the at boiling temperature the liquid become gas. Okay, gas TB at 1 bar. Then take the gas to the temperature of interest. Okay, so that is the entropy. First from 0 degree to melting temperature, and the phase transition happens, and boiling temperature the phase transition happen, and take to gas into temperature of interest. The all steps are very important. Okay, so 0 entropy at 0 Kelvin, this is 0 by that law. Okay, and 0 to temperature in then this is for cpdt, and for phase transition delta H fusion by T, like that. Okay, so you know the relations. Okay, delta S is positive for each of these process. The entropy must have its smallest positive value at 0 Kelvin. Okay, so every pure substance in its crystalline solid state, the entropy is 0. Okay, so that is the third law. Okay, we saw the Nernst heat theorem. What Nernst in 1905, when temperature becomes 0, the change in entropy becomes 0 for all isothermal process in condensed phase. Okay, Then the more useful formulation of Planck is the when the temperature above 0 Kelvin, the entropy also approaches zero. Okay, for chemically homogeneous substance in a perfect crystalline state. Okay, it works from statistical thermodynamics also is work perfectly. Okay, it is impossible to decrease the temperature of any system to 0 Kelvin in a finite number of steps. Okay, it is impossible. Okay, so we saw how. Okay, how do we can rationalize this statement? Recall the fundamental equation. Okay, for ideal gas, Cv equal to dt and pressure equal to RT, and substitute these two for du equal to Cv and pressure into this. Okay, then you got the relation, and you take the Ts this side. So here you see the ln T. Okay, if your T2 is 0, okay, then the ln 0 is infinity. Ln 0 equal to negative infinity. Okay, ln 0 equal to negative infinity. Okay, so here you see this. Here this is something negative infinity means this is greater than 0, but then this must be greater than the positive infinity. Okay, that is impossible. Okay, then only, so that is T2, you cannot go to the temperature 0 Kelvin. Okay, it is impossible to have a 0 Kelvin, but you can go as close as possible. Okay, so in the in Professor Kettler's go into the temperature of 10 power minus Kelvin, 10 power minus 9 Kelvin. So that's not, it is negative means 10 power minus negative means does not negative. Okay, so what is 10 power minus 19 means 0.0000001. Okay, 90 after 90 you got 1. Okay, so that is a positive value, not a negative value. Okay, you cannot approach 0, but you can go as close as possible. Okay, okay, so consider calculating entropy at 0 Kelvin. Okay, so this is the formula CPDT divided by T. Okay, so when the temperature approaches 0, the CPR must also approaches 0. Otherwise, you got infinity. Okay, 1 by 0 equal to infinity. So when temperature below temperature approaches 0, Cp must also approaches 0. Then only you got 0. Okay, entropy 0. Okay, you should know when temperature 0, Cp approaches 0, Kelvin also approaches 0. Okay, otherwise it become infinity. In fact, experimentally Cp is a function of temperature. Okay, it goes to 0 as temperature goes to 0 Kelvin. Okay, the above equation dt equal to dq by cp at constant at t is equal to 0 infinity, small amount of heat would result in a finite temperature rise. Okay, what say is, so here you see the relation dq equal to cp dt. Okay, so when the temperature when the at 0 Kelvin, when the temperature goes to 0 Kelvin, if you somehow manage to make 0 Kelvin, so if you somehow manage to 0 Kelvin, you will not be able to maintain the temperature because small amount of heat from a warmer jet will raise the temperature above 0. Okay, here this is the relation. Okay, dq equal to cp dt. Okay, at the temperature 0, when our temperature approaches 0, this is become 0. Okay, then the whole dq also becomes 0. Okay, to raise a temperature change. Okay, so what they say is when you approaching the temperature, the heat needed to change the temperature is very slow, approaches 0. The heat needed to raise the temperature approaches 0 means very tiny amount of heat is enough to raise the temperature above the 0. Okay, very nice. 0, approximately 0 temperature also leads to increase the temperature change. Okay, this is not going to 0, it approaches 0. This is also approaches 0. Okay, means very small amount of heat is enough to make the system above the 0 Kelvin temperature. Like that, if you take a system like that, if you take the system at 0 Kelvin, okay, then you should kept the system at a isolated system. So here the temperature should be higher than this. Okay, so then heat will flow here to here. Okay, if it is not in zero, if it is not in zero, the heat will flow from zero to and make the temperature greater than zero. So you cannot maintain the 0 degree temperature. Okay, you can make somehow make to 0 Kelvin, but you cannot maintain that temperature because you should the material used for the isolation is greater than the zero. So if you maintain this temperature is zero, okay, you should make another system. You should maintain this also zero. If it this maintains zero, you should also maintain this also zero. Otherwise heat will flow into the system. Okay, heat flow from hot source to cold source. So if you maintain something 0 degree celsius mean you should maintain this also 0 degree celsius. That is impossible. If you maintain this 0 degree celsius, you should also mention this. Like that you go to the whole universe to 0 Kelvin. That is impossible. Okay, okay, I think you understand this better. Okay, because it is very very important question. Okay, any disorder at a 0 Kelvin. So something like a violation of the third law, but it's not. Okay. So if you take delta S mixing, it is always greater than zero, even at 0 Kelvin. But it is a mixed crystal. Okay, so it is a mixed crystal, but not a pure substance. Okay, so the third law not violated. The third law says for a pure substance at a temperature zero, delta S is equal to zero, not a mixture. Okay, so here also the temperature not violated. For a impurity or defect in a crystal, the entropy greater than zero at 0 Kelvin. Okay, here also the third law not violated because it is impure. Okay, so then the orientation and the conformational degeneracy, like if you take CO in a crystal, some CO are different. Okay, then the entropy is greater than zero. Entropy greater than means some disorder. It is not order. Okay, some disorder. Okay, so this is also two orientation are possible. So this is also entropy greater than zero at 0 Kelvin. Okay, so these are called residual entropy. Okay, at 0 Kelvin, the entropy is residual entropy. Okay, what is the criteria for spontaneous change? Okay, so from the second law, you say class is inequality. Okay, dq by t surrounding. Okay, from the first law, you say du equal to dq plus dw. You put these two equation here. What is substitute dq for here? Okay, dq is d ds greater than dq. Okay, dq is less than dds. Okay, so if you substitute instead of dq by dt, then it is less than zero. Okay, it is less than zero. Okay, delta u pdv minus dds because it is somewhat greater than the dq. Okay, then it is less than zero. Okay, the whole process, this is very very important equation. The equilibrium, like if you take an isolated system in Q W equal to 0, D equal to 0, delta V also 0. Then you can dV cancel, du cancel, you get this relation only. So here negative D temperature, delta S should be positive. Then only the multiplying these two get term, you get a less than 0 means negative value. If delta S is negative means what happens? Negative into negative, you get positive. Okay, so delta S should be positive, greater than 0. That is the criterion for isolated system at constant internal energy and volume. Okay, at a constant entropy and volume, what happens? You see here at a constant entropy and volume. At constant entropy here this becomes 0. At constant volume this becomes 0. So du become less than 0. Here du is equal to less than 0. This is the criterion for spontaneous at constant volume and entropy. Okay, at constant S and V, the equilibrium when the energy is minimized. Okay, so like that, the difference in delta U must be less than 0, meaning that if you plot internal energy versus the process of reaction. Okay, reaction, then the internal change in internal energy must be less than 0. Okay, so if it is this is initial state, and this is go to final state means if you take here 5, here 10, minus the final minus initial is 5 minus 10 equal to minus 5, that is less than 0. That is the du. Okay, du is nothing but difference from final to initial. Okay, always difference is final from initial. Okay, that is the conversion. Okay, um, then negative sign. Okay, so the change in the for spontaneous process, it goes like this. Like if you take a ball in this bowl, if you take, imagine this is like a bowl, then if you put a ball like this, it goes to here. This is the equilibrium state. Here there is no change in internal energy, du equal to 0. If you put a ball in this, it goes reverse direction, because this is the reaction direction. If it goes reverse means a is a to b. Okay, so this is a to b. It is reverse mean it goes reverse reaction is spontaneous, b to a. Okay, at constant s and b. Okay, like that at constant h and p external, what happens, and this is nothing but delta h. Okay, so constant h means these two become 0, and now you got only the t surrounding and dds. Now also ds should be greater than 0. Okay, now we saw something experimentally viable, constant temperature and constant volume. Okay, so these are not viable. Okay, so experimentally is somewhat more complicated to make constant entropy, or at constant entropy or constant enthalpy. That is somewhat experimentally difficult. Okay, that is not meaning that is not possible. um, it is possible, but it's somewhat complicated. Okay, okay. But making temperature and volume constant is possible. Okay, that's making temperature is the surrounding and make a closed system. So then the constant volume, then the relation become constant volume. Then the relation goes to du minus tds. What is the here is something calculation missing. Okay, so if you expand this, you what get du minus TDS. Minus TDS means TDS minus S dt. Okay, that is this. So at a constant temperature, this is become 0. Then you got du minus TDS. Okay, that is this. Okay, so the u minus ds is A. Okay, that is the Helmholtz free energy. Okay, Helmholtz free energy is that is dA. Okay, dA. If this is A means dA. dA should be less than 0. That is the criteria for spontaneity. The Helmholtz free energy should be minimized. Okay, minimized. How much minimized? It should be the Helmholtz free energy should be minimized. How this is Helmholtz free energy means it should be minimized. Okay, like now we come to the most important and applicable constant at constant temperature and constant pressure. Okay, you see then most of the reaction in the world. Okay, it constant occurs in constant temperature and pressure, constant atmospheric pressure, constant atmospheric temperature. And if you take our body, the temperature of our body is maintained at constant temperature. Our pressure inside our body also maintained at constant pressure. So all biochemical reaction and all the chemical involved in the nature also constant temperature and pressure. Okay, this is the most important. Okay, and constraint. Okay, then now the formula is the same formula. Okay, du equal to pdv minus tds less than 0, and you take this constraint, you got this. Okay, u plus pv minus ts. Okay, this is the gives free energy. Okay, this is gives free energy. U plus pv minus ts is the gives free energy. Okay, you can write is in another form also. Okay, because a is nothing but u minus ts and h is nothing but u plus pv. Okay, so same. Okay, so the concept is delta e should be negative, when negative or less than 0. That is the criteria for spontaneous process at constant temperature and pressure. Okay, take g, that is very important. Okay, okay, for spontaneous process less than 0, at equilibrium means equal to 0. Greater than 0 means the reverse process is spontaneous. So I already told the example. Okay, it's positive means spontaneous, negative means the reverse process is spontaneous. Okay, equal to 0 means it is attained equilibrium. Okay, okay. So this is okay. So this is a four fundamental equation. Okay, these are simple equation. You using first law and second law, you can derive all these equations. Simple mathematics. If you are interested, you try out all these equations. Okay, and you see A is a function of temperature and volume. You can integrate first with respect to temperature and with constant volume, and with respect to volume and constant temperature. Now you got this is the nothing but minus s. Okay, you see the equation here, dA equal to minus s dt. Okay, dt is here, but then this is the delta s. Okay, like that you can find all these are simple mathematics. Okay, relations, Maxwell relations also a mathematical relation. Okay, you differentiate with respect to two times. Okay, if you first respect to temperature then respect to volume is same, first respect to volume then with respect to temperature, that is same. Okay, and that is the one of the main property of the partial differentiation. Okay, the Gibbs free energy is this example of, if you take Gibbs free energy. Okay, dg equal to v dp minus s dt, dg equal to minus s dt plus v dp. Okay, if we take dg equal to vdp minus s dt. Okay, now how to the van der Waals equations are derived. Okay, so see Maxwell equations. Okay, so first differentiate with respect to temperature, pressure. Okay, 2g divided by dou p at a constant temperature. At a constant temperature this is become 0. Okay, dt becomes 0. Then you got what, v only. So v into dou by dou p into dp equal to 1. Okay, so equal to 1. Okay, so you got v. Okay, so differentiating with respect to pressure at constant temperature, then differentiating with respect to now pressure, then differentiating with respect to temperature at constant p. What happened at constant b, this is become 0, this is become 0, and you got negative s. Okay, then differentiating with respect to same. Okay, if you take the first reaction, dou g by dou p at constant d equal to v. Okay, dou g divided by dou p at constant t equal to p. Then differentiate both sides same. If you differentiate both sides same, then nothing change. Okay, if you differentiate with respect, first you differentiate with respect to temperature, then pressure, then differentiate with respect to temperature at a constant pressure. Okay, then you should also, if you do it something to the right, mean you also do it from the right side, means nothing change. Okay, if you multiply 2 with 5 equal to 2 into 5. If you multiply two side same, means nothing changes, because the two cancel out, the equation nothing change. Okay, like that. Then uh, like that, if you differentiate with respect to here, differentiate with respect to temperature. Okay, at the constant pressure. Okay, so this is one of the relation. Okay, here I already told you, this is dou g by differentiating delta g with respect to pressure at constant temperature, then with respect to temperature at constant pressure. Okay, okay, now you see this relation, you take this relation, dou g by dou t at constant p equal to minus s, dou g divided by dou p at constant t equal to minus s. Then now differentiate with respect to temperature. Here first this is pressure, then temperature at the whole system at the constant p. The right side also differentiate with respect to temperature at the constant p. The left hand side the two are equal. Okay, that is the partial differentiation. Okay, if you something differentiating with respect to pressure and temperature is same as something differentiating with respect to first with respect to pressure with the temperature. If the left hand side are equal, means the right hand should be also equal. So the right hand is dou v by dou t at constant b equal to dou v by dou p at constant v equal to minus dou s by dou t at constant p, minus dou s by dou t at constant b, dou t at constant b. Okay, this is the Maxwell relation. Okay, so partial differentiation is nothing but if you take this is u and this is, if you take like this internal energy, this is internal energy means, and take like that. Okay, here what are the variables? Temperature and pressure. Okay, this is temperature, this is pressure. Okay, something internal energy is function of two. Okay, if you'd like if you, this is the initial means, this is the final. Okay, so if you take temperature like that, if you change the temperature first then change the temperature next, you got at constant if you take this is the at constant temperature, this is at constant pressure. Okay, temperature and constant heat, then if you add these two you get the final final entropy. Okay, that is du equal to dou v dou dou u divided by dou p dp at constant t plus du equal to, if you take u as a function of temperature and pressure, then du equal to, first you take the temperature. Okay, differentiating with respect to temperature at the constant p. Okay, dt plus dou u divided by dou p at constant temperature dt. Okay, that is the partial differentiation. This is the this is differentiation, but this is partial differentiation. Okay, so nothing but because it is a variable of two variable here means, some you should take some variable constant and change the other variable and take the other variable and like that. Okay, so that is the process. Okay, you should know these relations. Okay, if you know this relation, this is the nothing but yeah. This is how the Maxwell relations are derived. Okay, you can derive for all the four equations. You will definitely enjoy it. Okay, like that. These are mathematical calculations. Okay, if you try it, you will understand better. For if you take here, okay, for ideal gas, if you here nothing change. Okay, so if you take the du equal to tds minus vdp, same formula, and here they differentiate with respect to volume at constant temperature. Okay, differentiating with respect to volume means you got tds become dou s divided by dou v at constant temperature, and here also. So what is du formula is I wrong? Du is tds minus pdv. Okay, so sorry, forgot the formula. So du equal to tds minus pdv. Okay, so with respect to volume means this become 1. Okay, so negative p, and so you get this relation. Okay, so what happen is when this is dou p by dou t at constant v, so you know the relation. So all are these relations between these two and two. Okay, we derived earlier. Okay, So then what will happen for ideal gas? P is nothing but nRT divided by V. Okay. So differentiating with respect to temperature mean this become 1 and nR by V. Okay. nR by V is nothing but P by T. Okay. So nR by V means P by T. So if you substitute P by T here, you get P by T, T cancel, P minus P equal to 0. Okay. Like that for entropy also, enthalpy also. We know this relation earlier. Internal energy does not change when volume change, and enthalpy does not change when pressure change. Okay. Okay. So that is for ideal gas. But for van der Waals, what happens is does not become zero. Okay. So this is van der Waals equation. Same. You should same the follow the same procedure. You got this is not equal to zero. And the special role of G is what happen. If you know the gives free energy at temperature and pressure, you know everything. Okay, like if you using these relation, you know the S N B, because here temperature, pressure, and the delta G only. Okay, so if you know H is equal to G plus ds, from that you can put the S and this. Then you now also you get only gives free energy, temperature, and pressure. You got H. Okay, like that from only you know this value, you can know everything. Okay, that is the power of mathematics. Okay, why we need all these mathematics. Okay, so if you find something, you can calculate something. That is the power of mathematics. That is why mathematics is the queen of science. Okay, okay, try all these how it comes from. Okay, it will be interesting mathematics. For liquid and solid, volume is very small compared to gas. Okay, so if you take 1 liter of gas, it occupies huge volume. But if you compress it to a liquid, it becomes very small. Okay, so the second part becomes zero. So then the gives free energy is a function of temperature only. Okay, for ideal gas, delta G equal to RT by P. Okay, instead of P, you put only you can use the relation for ideal gas only. Okay, otherwise don't use this relation. Don't put instead of P, don't put RT by V. Okay, only when there is ideal gas you can substitute this equation. Okay, and the real gas you cannot use this equation. Okay, and that's why for ideal gas relations are different from real gas. Okay, so for ideal gas you put just to put the PV equal to RT by V, you get the relation. Just like if you convert p bar into one bar means p bar. If you take p1 equal to p bar equal to 1 bar means you get p. Okay, you know these relations. So delta S is nothing but differentiating delta G with respect to temperature at constant T. So this is delta G. Just with respect to temperature mean this become 1. Okay, 1. T become 1. Okay, not 0. Okay, not 0. T become 1. So RT ln P. Okay. If you know the delta G means, if you want S means just differentiating with respect to temperature and put the negative sign. Okay, don't forget to put the negative signs. Okay, so far we worked with fundamental equation for a closed system with no composition change. How does this equation change if you the composition of the system change? Okay, like in a chemical process or biochemical process, the composition are changed, marks exchange happens between our system and the surrounding. Okay, what happens if you take a two component system, delta G, temperature, pressure N1 and N2. This is delta G. Okay, so differentiating means these are function of four factor. Okay, so then you could partial differentiate with respect to one by one. Okay, first with respect to temperature and dot T and dt. Okay, then with respect to, and take the others constant, pressure N1 and N2, and then differentiating with respect to pressure and take temperature N1 and N2 constant. Then differentiating with respect to N1 and take temperature, pressure, and N2 are constant. And differentiating with respect to N2 and take temperature, pressure, and N1 are constant. Okay. This is nothing but minus delta S. This is nothing but V. But these two are the chemical potential. Okay. How the gives energy change when the component change. Okay, at constant pressure and temperature and other components are kept constant. Okay, Mu1 is an intensive variable, so don't forget it does not vary with the size. And this give you a new set of fundamental equation to the open system. Just to add this extra term, okay? A summation of I mu I dni, okay? Meaning you should chemical potential of all the I component and dni change change of ni, okay? Change of moles, okay? That is the so so how this I equation come from? This is the equation, okay? This equation is the same, okay? So this is minus s dt minus v dp mu1 dni mu2 dn2, okay? That is the equation. You see minus s dt vdp, and we put mu1 dni n1 plus mu2 dn2 for two component system. For many component system you add all, okay? Any number of components just add, okay? Like that you can derive for du dh dn dA, okay? And for these are partial molar quantities, okay? So for differentiating with respect to g at constant ni and s at constant temperature and pressure, constant entropy and pressure, constant entropy and volume, constant temperature and volume, these are all equal, okay? All equal means these are all equal, okay? At equilibrium, the chemical potential of a species is same everywhere in the system, okay? Now let's take a system has a one component but two parts, okay? Like water, okay? Like water, liquid phase and solid phase. So like water, liquid ice, liquid water and solid water, okay? That is ice, okay? So otherwise, other example is take salt water in your water. If you take a beaker and you take a water, here salt water, and it is a porous, okay? This porous means this is water means the water go into the salt solution, you know, this is osmosis, like, okay? um, if it reverse means reverse osmosis, this is osmosis, okay? Consider for the example, find delta G for this process. Here, consider DNA amount of compound from phase to phase B. If you like, if you take ice and in your water, some amount of ice melted and go into the water. Okay. So if you take this transition, DNA equal to minus DNA, TB at phase V and phase A. Delta G is nothing but mu 1B by mu A DNA. Okay. The whole equation should be if you write the whole equation and the negative, the all terms are cancelled out, only these two terms are not cancelling out. Then you need you saw when the chemical potential of A is higher, okay? A is higher means the delta A is less than 0. Then spontaneous conversion of this is A, this is B, okay? Conversion of A to B happen, ice melting to water. If chemical potential of B is higher, okay, B is higher means it is become positive. Positive means the reverse is spontaneous. Then the B to A, okay, the ice water become you if you observe, take a bath of water and put a water, what happens you observe, then find which has the more chemical potential. Okay, the answer is ice has more chemical potential, okay, than water. Okay, at equilibrium, these two are key at chemical potential are same. Okay, like what happened this when the 0 degree Celsius and 1 bar, ice and water are become equilibrium. Okay, equilibrium. The two become equilibrium, meaning that why the ice does not melt. Okay, maintaining temperature 0 degree Celsius, ice does not melt. Okay, so okay, liquid water and ice in equilibrium example. The temperature is 0 degree Kelvin, 0 degree Celsius, and the pressure is 1 bar. Okay. If it is something greater means like chemical potential greater means it's like a top of a hill. Okay. Top of a hill. Chemical potential low means bottom of the hill. Water flows from top to bottom. Like substance goes from high chemical potential to low chemical potential. Like that hill. Okay. If it is reverse means the reverse process happens. Okay, A gives to B. Okay, so chemical potential B is higher. Is means that is the chemical potential like that. Like if you take a salt water and water solution and water, then the solution has water has the great chemical potential than the solution. Okay, so then only water goes into the solution because high to low. This is high, high to low. Okay, go to low, low chemical potential. Water, pure water go into the solution. That is the osmotic. So what we call osmotic pressure. Okay, downhill drive to equilibrium will be the guiding principle for our study of phase transition, chemical reaction, and biochemical process. Okay, the mu A is nothing but the partial molar Gibbs free energy. Okay, because the variation of Gibbs energy with respect to molar concentration. If you add all these, you get the G Gibbs free energy. Okay, this is partial molar Gibbs free energy. If you all add partial, you get the total Gibbs free energy. Okay, let's prove this equation. Okay, simple. If you take n lambda mole of n1 and lambda n2. Okay, differentiating with respect to lambda. Okay, and you take lambda of g. Okay, that is partial. Okay, that is partial. Then with respect to temperature, mean this is become 0. This is delta g become delta g because delta 1 become 1. If you respect to delta lambda means this is also constant. Okay, become 0, and delta g with respect to dni. Okay, then lambda n1 and lambda n2. Okay, so first you differentiating delta g with respect to lambda 1 and lambda 1 with respect to lambda. Okay, so then you got the relation. Okay, so this is nothing but the mu1 and this is nothing but the n1. Okay, this is nothing but n1 because the lambda cancel out. Lambda with respect to lambda means you got n1, and differentiating delta g with lambda n1 is nothing but mu1. Okay, because dou g divided by dou n is mu1. Okay, so mu1 n1 plus mu2 n2 equal to g. Okay, so this is a relation. Okay, okay, we can prove partial molar quantity similar. Okay, for all. Okay, but don't forget the constant temperature and pressure. Okay, normally delta A is the at constant temperature and volume. Okay, mu I equal to dou A by dou Ni at constant temperature and volume. Okay, but so don't confuse with this and with this. Okay, total uh, uh, Helmholtz free energy and total enthalpy and total internal energy. Okay, don't confuse with the relation with this. Okay, this is partial molar Helmholtz free energy. Okay, this is partial molar enthalpy, this is partial molar entropy. Don't confuse with the this. Okay, if you take A and B mixed and A pure. Okay, what happens? This is chemical potential mixing at equilibrium. The chemical potential of mixing and the chemical potential of pure is equal to. Okay, um, what is the chemical potential of pure A? Okay, equal to P total. Okay, P total into XA is nothing but PA. Okay, partial pressure of A at partial P. Okay, so substitute for P total. You know the relation mu A equal to nothing but mu A not means at a standard condition plus RT ln P. Okay, so here instead of P you substitute P total divided by XA. Okay, and if you learn something multiplication means you can separate the equation into positive sign, positive RT ln XA. Okay, now you see this is the for pure substance because for pure substance P is nothing but P total divided by P naught. Okay, for this is then the equation become uh, delta A mixing equal to delta mu of pure plus RT ln XA. Okay, here XA is less than 0, less than 1 means this is negative. Negative. Okay, so negative means the pure entropy in chemical potential is always higher than the mixing. Okay, that is there is the heart of reflection of entropy, because in the mixing there is entropy, more entropy than the pure. Okay, because entropy tends to become more disorderliness, but chemical potential become more less. So the chemical potential A in a mixture is always less than the chemical potential of pure A at the same total pressure. Okay, this is the heart of the reflection about entropy. Okay, okay, I think you understand everything. So thank you so much for watching.